In this video, we're going to talk about confidence intervals for percentiles without knowing what the underlying distribution is to start with. So let's start with y1 out to yn be the order statistics associated with the random sample x1 out to xn. So remember, the order statistics again are you select a random sample and then you put them in order. That's what we mean by the less than signs in there for the order statistics list that we have there at the beginning. We're going to assume that the distributions that we are talking about are continuous, but that's the only assumption that we're going to make. That was why I didn't have any less than or equal to there. Certainly if you have a discrete distribution, you could have equals, but that's not what we're going to be dealing with in this case. We're just going to assume that everything is continuous. All right, so if we know the distribution of the x of i's, or in particular the underlying distribution where you've drawn your random sample, then we can figure out the PDS for each y sub I. We've done this before, but just as a reminder, say we look for the nth order statistic, so the maximum, then remember we've done this trick where we look at the probability of the y sub n being less than or equal to y. This is the cumulative probability, the cumulative density function, pardon me. This is equal to the probability that all of the x sub i's are less than or equal to y. Certainly if the maximum is, they all have to be. Using the independence of the random sample, this is just the cumulative distribution function for the x raised to the nth power. So then if I want the PDF, I just differentiate. We've done things like that before, and you should be able to see on page 431 how to calculate the PDS for all the ith order statistic y sub I, whichever one you're talking about. Now, again, if you know the distribution and you know the PDF, then you can get confidence intervals using your PDF for whatever percentile you would like. But we would like to do this without knowing the underlying distribution. Certainly, in general, if you take a random sample from some distribution, you don't know what the distribution is. You might be able to do some goodness of fit tests on certain types of distributions that it might look like, but you don't know what it is. So we're going to assume that we have no idea what the distribution of the population is to start with, but still we're interested in figuring out confidence intervals for percentiles. So we refer to these as distribution-free confidence intervals. That's what we're actually calculating here. So we're going to construct confidence intervals for the percentiles, which we're going to denote pi sub p. So p is the probability associated with whatever percentile we're talking about, and we just use pi to denote that we're looking for that particular number associated with that probability. And we're going to use the order statistics. So, in particular, if I take, without worrying about the order necessarily, but in general, if I take a random observation from a distribution, then the probability that that random observation is less than the pth percentile, the pth percentile is p. That's how we define the percentile, right? It splits the distribution into p below and 1 minus p above, if you think about them as percents. Now, we can think of each of these y sub i's as independent observations and identical trials, because we're doing random sample. So we can use a binomial distribution, namely, if we have n order statistics, or we have n trials, and the probability that p is that any individual one is less than the percentile we're looking for to form our interval. All right, so we want an interval that likely contains our pi sub p. So we're going to consider some y sub I and some y sub j. The y sub I will be below, the y sub j will be above, and we want this probability to be 1 minus alpha, like we've done for any other confidence intervals. All right, so in order for this to happen, we need to have at least I of the observations to be less than the percentile that we're interested in, because we want y sub I to be less than that. That means y sub I all the way down to y sub 1 have to be less than. And if we want y sub j to be bigger than, then at most y sub j minus 1, at most j minus 1 observations, so the j minus 1 and below can be less than the pi sub p. So to calculate this probability then, if we want at least I of them and at most j minus 1 of them to be less than pi sub p, then we do the sum of our binomial PDF where we're looking at being less than pi sub b as being our successes. So this is going to be our probability. This is going to be our 1 minus alpha p. So this is the part that we're going to play with to see what the alpha is for our confidence level, if you will. All right, so to make this interval as symmetric as possible, whatever that means, but to make it as symmetric as possible, we're going to use n plus 1 times p to estimate where the center of the interval should be. So let's think about why we would do this n plus 1 times p. So for example, say we're interested in a confidence interval for the median, then our p is 0.5, so we would use the n plus 1 over 2th order statistic for a point estimate for the median. That's exactly what you do, correct? When you do a median of a list of numbers, you take the high, you look at what's directly in the middle in your data set. So you would list them from 1 to n, and you take the n plus 1 over 2. That's the thing that's in the middle. So do that in general for any probability, and you can get the point estimate for the pth percentile. All right, so then we're going to choose I and j that are equally apart from n plus 1 times p to construct the intervals. So as an example here, let's say we have the list of numbers 2 up to 25. This is our list. And I want to get a confidence interval for the 30th percentile, so pi sub 0.3. So a point estimate for that will be, there's 9 elements in my list, so I do 9 plus 1 times 0.3 gives me the third order statistic, which is 8. So this is going to be the center of my interval, the 8. So there's a couple of intervals that I can do if I'm going to make 8 the center and just use numbers from my list. I can go 5 and 10 to be a symmetric interval around the 8, because that's y2 and y4 around y3, or I can do 2 and 12 around 8. So let's see what confidence level we would have for those two particular confidence intervals for that percentile. All right, so using the y sub 2 and the y sub 4, we get the interval from 5 to 10. This is going to be a 1 minus alpha confidence interval, and so we need to calculate what the 1 minus alpha is. We need at least 2 that are less, but at most 3 that are less than 8. In this case, the 30th percentile. So we would do 9 choose k, 0.3 to the k, 0.7 to the 9 minus k, plug in 2, plug in 3 for k, and simplify, and you get 0.5337. So this would be a 53.37% confidence interval. Not a great confidence interval. All right. So let's expand it to y1 and y5. So then we get the interval from 2 to 12. Is going to be another 1 minus alpha percent confidence interval for what? For the 30th, I should write pi sub 0.3 instead of pi sub p here. But this is going to be a whatever the percentage confidence interval is, where our 1 minus alpha in this case, well, we need at least 1 to be less than the 30th percentile. So we'll start our sum at 1. And at most 4, because we want the y5 to be above it. So do that same calculation like we did above. We're just going from 1 to 4 instead of 2 to 3, and we get 0.8608. So the interval from 2 to 12 is an 86% confidence interval for the 30th percentile. So a great, not a great confidence interval, obviously, but if you had more and more data points in your sample, you get a better and better approximation than for your confidence interval for that particular percentile. Notice again, we didn't have any underlying distribution that we drew the data from. We just used our knowledge of the order statistics and what it means to be a percentile to calculate these confidence intervals with the help of the binomial distribution. So we'll spend some time in class doing more examples with bigger data sets and perhaps using the normal approximation to the binomial to help us figure out some confidence intervals as well.